Hello and welcome to the videos for Math 139 College Algebra. In order to best follow along with these video lectures, my recommendation is that you have a copy of the Math 139 course pack or course notes that are available from the Jackson College bookstore. It'll be a lot easier to follow along and take notes if you have these outlines to work from. When you get your course pack, you should find that the first couple of pages are actually just a table of contents. So you'll note that we'll begin the semester talking sort of in general about the really important mathematical concept of functions. And from there we'll go on to talk about a whole lot of different types, specific types of functions. Linear, quadratic, higher order polynomials, exponential and log, rational, and then finally radical over the 7 units of this course. That said, we are going to start today by taking a look at Unit 1 on exploring algebraic functions. One of the things I want to mention before we actually start the first section is you're going to see in the first 3 sections of this course an approach, or 3 approaches really, that will recur over and over again throughout the semester. As we look at things in this class, we're going to be looking at algebra numerically, graphically, and analytically. And our first 3 sections will really outline what each of those approaches is all about. When I talk about approaching algebra from a numerical perspective, I'm usually talking about using things like tables of values, maybe ordered pairs, things like that. Looking at algebra from a graphical perspective, kind of a dead giveaway there, the word graph's right in the name, right? But this, of course, is when you're going to be looking at graphs of functions. And then the third method, the analytical method, is actually the one that most people think of first when they think of algebra, but it's really not all of algebra. These are the formulas, the algebraic equations with the letters and numbers, all of that. So expressions and equations. So again, we will take 3 separate times here to investigate what it means to be a function from each of these 3 perspectives. This particular video is going to concentrate on section 1.1, which is our numerical approach. One last just sort of general thing I'd like to mention to you before we dig into some problems is that the whole concept of a mathematical function is really fundamental to all of algebra. And so the things that you learn in this chapter are absolutely the foundation for everything else you're going to do this semester. Also, the approach that we will try to use in this class is going to be as much as possible an applied approach. So rather than just seeing letters and numbers and lists and tables, we'll try to put things into context. And my hope is that when you're done with this class, you'll have an appreciation for not just algebra for itself, but why algebra is important and how it can be used to help us interpret the world around us. All right, so I've kept saying this word function over and over again. What exactly is a mathematical function? Well, a function is a relationship between 2 variables that follows just one really important rule. Each value of the input variable can lead to just one value of the output variable. Every input has exactly one output. So, in this section, we're going to take a look at how this rule is expressed numerically, and I'm going to start with the table of values here in example 1. By the way, we'll be looking at a little bit of vocabulary that's associated with functions as we go along here. All right, so in my table here, I have a table that shows if you are at the store buying oranges, the number of oranges you buy affects, of course, the price that you're going to pay, the total cost in dollars. The number of oranges, I'm using the letter N to represent. So that's what's called my input variable, or more formally, the independent variable. So in this case, the independent variable or input variable is the number of oranges, N. In a table of values, the input variable will always appear on the left-hand side. Secondly, we have our output variable. Again, formally, this has a name. It's called the dependent variable. And in this case, the output or dependent variable is C, the cost of the oranges. Hopefully that kind of makes sense. The independent variable, you get to decide how many oranges you're going to buy, but then the cost depends on the number of oranges you selected. All right, so based on our definition that each value of my input variable can only have one value of the output variable, does it make sense, at least in this particular store at this particular moment, that this relationship is a function? And I'm going to say yes, right? It wouldn't make sense if I buy 4 oranges and pay $2.40, and the guy behind me in line buys 4 oranges and they only charge him $2, right? Every input, the number of oranges, can only have one output, the cost. Again, assuming we're in a particular store on a particular day here. So, is the relationship between N and C a function? Yes. Each value of N can only have one value of C. And when you're asked a question like, why is something a function or not a function, your answer should always revolve around this idea that every value of the input can only have one value of the output. Mathematically, we use this language. We say that C is a function of N. And notice that this statement is in a very particular order. We always say that the output or dependent variable is a function of the input or independent variable. So even if I hadn't seen this table of values up here, if somebody said C is a function of N, just that simple statement tells me which variable is the output and which variable is the input. All right, in mathematical symbols, we can actually write this statement using what's called function notation. Every function has a name. Sometimes we'll tell you what the name is, other times you can make it up. Here's a couple of options in this case. I could write C is a function of N by saying C equals f of N. In this case, I've chosen to give the function the name f. F for function is a really common thing to use. You'll see it a lot. Another option, I could write C is a function of N, but notice this time I've given the function the name C. Both of these statements really say the same thing. C is a function of N. We've just given the function different names. in the two examples. Again, unless you're told, you can pick any function name you want. I have a tendency to really like this one. I like using the dependent or output variable as the name of the function because it reminds me what I'm talking about as I work with my function. But either one absolutely works. Or you can make up an entirely different name if you really want to. One more thing that I want to mention about function notation. Most of you, in your past experiences with algebra, have seen the idea that parentheses can be used for multiplication. Like, for example, when you see something like this, that really means 3 times 4, right? With function notation, these parentheses do not mean multiplication. Okay? This is a specific notation, and again, you read it F of n or C of n. What we're saying is the dependent variable is a function of the independent variable. So this language right here. Right? So don't think of it as the parentheses like multiplication. In this case, the parentheses indicate function notation. All right, one nice thing about function notation is we can actually use it to give specific associations between our inputs and outputs. So I'm going to make this a little bit bigger so we can see the table here at the same time as these questions. In this little example, we're asked to find C of 4. Again, not multiplication, it's function notation. C of 4. What I'm really being told here is the value of the input, n, is 4, and they want me to tell them the value of C, the output. So I just go up to my table and say, okay, if the input is 4, the output is 2.40. Now, I didn't ask you to do this here, but I'm going to write it down anyway. We could then write a sentence that gives the specific association saying, if we buy 4 oranges, the cost will be $2.40. So again, one of the things that I really want you to get used to is this idea that mathematical function notation can really be a shortcut for something that has a very specific meaning in the context of the problem. Let's go ahead and try this for C of 10. Take just a moment, write down what you think the answer is, and then write a quick sentence. By the way, every now and then I'll pause to give you time to try one on your own, and I would encourage you just to use your pause button if you need a little bit more time to do that. All right, so in this case, they again told me the input, n is 10. And so I go up to my table. When n is 10, the output C is 6.00. And what that really means is that 10 oranges are going to cost $6. This idea of taking a mathematical statement and writing like a real world or interpretive sentence is something you're going to see a lot in this course. So it's something to start getting used to. When you're asked to interpret something in the context of the problem, I'm not just looking for the generic when n is 4, C is 2.40. I'm looking for what does that really mean? The 4 oranges and the cost of $2.40. So interpreting in a real world context is something we'll do quite a lot of. All right, let's go on to example 2. Don't put that too far away because we're actually going to come back and take another look at that first example again in a little bit. But here in example 2, we're told that we take a bottle of water out of a cold refrigerator and leave it at room temperature. Naturally, it's going to warm up as it sits there, right? Each of the following ordered pairs down here is of the form m, t, where m represents the number of minutes that the water's been sitting out of the refrigerator, and T is the temperature of the water, units of degrees Fahrenheit. So here are the ordered pairs that I was given. Every single one of those ordered pairs is the same format. They're all m, t. All right, so the first thing we're asked, is the relationship between m and t a function? Well, remember, the rule is every input just has to have one output. And we can really see that. When m, the minutes, is 0, t, the temperature, is 35 degrees, and I don't see any other temperature for 0 minutes. In fact, it wouldn't even make sense, right? At any particular moment in time, the water can only be one temperature. So I'm going to say yes. Each value of the input m has exactly one value of the output, t. All right, we are supposed to specify independent and dependent variables. By the way, easy way to remember this, independent is the input. So independent just like with table of values, in ordered pairs, the one on the left is the input, and that's our m, our minutes. M, the number of minutes. And dependent, again, just like the table of values, the one on the right is always the dependent, so that's going to be T, the temperature. This process of explaining what the variables are and what they mean is actually called defining the variables. And if you have a problem that says define your variables, that just means tell me what letters you're going to use and tell me what each letter represents. All right, we want to express the function, the relationship here in words. Blank is a function of blank. And just a reminder, when we use that, it's always the output is a function of the input. So the output, T, is a function of the input, M. Now I could write that relationship using function notation. I could say T, my output variable, is a function of M. I could write that as f of M or g of M, but I'm just going to choose to write it as T of M. Again, I really often like to use the output variable as the function name. It just reminds me what I'm talking about. All right, it then just says choose two of these ordered pairs and write function notation for them and explain what they mean in the context of the situation. So I'm going to start with the 035. I could say T of the input 0 is equal to the output 35. And that means that at 0 minutes, in other words, at the moment you take the water out of the refrigerator, its temperature is 35 degrees. So 0 minutes after water leaves the refrigerator, the temperature is 35 degrees Fahrenheit. All right, pick one more When I actually do this, I'm going to choose this one just if you want to do the same one, but if you want to do a different one, that's fine too. Again, I'll encourage you to pause for a moment and try and do the same thing for one of the other ordered pairs. Again, I'm going to choose 3057, but you can do any of them. I'll give you a moment to try that. Again, pause if you need more time. All right, the function notation would be T of the input, 30, is equal to the output, 57. My input, my 30, was the number of minutes. So 30 minutes after the water leaves the fridge. The temperature at that point is 57 degrees. All right, hopefully the idea of function notation is kind of clicking into place a little bit and what it tells us. You can practice on any of the other ordered pairs that we didn't do if you'd like a little additional practice here. All right, example 3. The heights of 6 children attending a preschool are measured, and the results are shown in the table down here. Is height a function of age? First of all, notice that the way I asked that question is consistent with the way the table is laid out, right? The way the table is laid out, the age, which I think I'm going to call A, is on the left, so it should be the input or independent variable. The height, which I think I'll call H, is the output or dependent variable. And now notice what I asked. Is height, the output, a function of age, the input? That's always the way that we phrase that idea. All right, well, having said that, let's see if it is. In this case, are you thinking no? I hope so. Let's look at the reason. Here are 2 children who are both 3 years old. So I have the input 3 in my table twice. And yet notice the 2 3-year-olds have different heights. Not uncommon, right? But it does mean that I'm not looking at a function here. Height is not a function of age. Height depends on other things besides just the age of the child. There are other examples here. You have 3 4-year-olds at this preschool, and they all have different heights. So no, in this case, there are inputs that have more than one output, so this is not a function. And again, explaining why. Some inputs have more than one output. As we've already illustrated with kind of the color coding in the table there. All right. So far we've seen 2 examples that were functions, right? Example 1 with the oranges and example 2 with the temperature of the water. I'm going to talk a little bit more about those 2 examples to wrap up our first section here. There are 2 types of functions that I'd like us to get to know and recognize: discrete and continuous functions. Here's how you tell them apart. In a discrete function, only specific values of the input variable can be used. It wouldn't make sense to talk about intermediate values between the allowed values. In a continuous function, it would make sense for input values to take on all real numbered values, intermediate values, or at least those between some lower or upper boundary. So let's take another look at example 1 and then example 2, and we're going to decide in each case, is it continuous or is it discrete? In example 1, our input was the number of oranges, n, right? It would make sense to buy 1, 2, 3, 4, etc., a whole number of oranges. But intermediate values like 1.4 or 7.5, that wouldn't make sense. You can't buy 7.5 oranges, at least not most places. So I'm going to say the oranges example, this is a discrete function. Really only whole numbers make sense as inputs, not all the fractions and decimals in between. So in example 1, we're going to go with discrete. Our input n, the number of oranges, really must be a whole number. Right? The fractions, the decimals, the in-between values don't make sense. Now let's look again at example 2. This is our water taken out of the fridge, and our input variable here is the m, the number of minutes. Now I happen to give us 0, 10, 20, 30, and 40, but do intermediate values make sense here? Not only 0, 1, 2, 3, 4, 5 minutes, which would also make sense, but what about 1.5 minutes or 7.25 minutes? Those make sense too, right? You could measure the temperature at time 7 1/4 minutes. You could measure the temperature at 10.5 minutes, right? So in this case, I would say this is a continuous function because all of the in-between values, all of the decimals, fractions, make sense as inputs for the number of minutes. Our input m, the number of minutes, could be a fraction or a decimal, and it would still make sense to ask what the temperature would be. A lot of times the discrete versus continuous isn't so much a mathematical thing as it is just a real-world understanding of what makes sense in the context of our problem. All right, one more pair of definitions to wrap up this section. Domain and range. The domain of a function is the set of all possible values of the input variable. All the possible inputs form the domain. The range of a function is the set of all possible values of the outputs, or dependent variable. So domain, all the inputs, range, all the outputs. We're going to one more time go back and revisit examples 1 and 2 and talk about domain and range. So in example 1, in this chart, I've got specific values, the number of oranges here, 1 through 10, but really technically you could buy no oranges. You could buy 1, 2, 3, 4, 5, all the way up, I suppose, technically to infinite many oranges, or at least as many as your grocery store happens to have. But you can't buy fractional numbers of oranges. So I'm going to say for all practical purposes here, my domain would be 0, 1, 2, 3, 4, 5, etc. You'll notice I use the braces to enclose my list of values that could be included in my domain. All right, what about the range? Well, let's see. The range was the costs. And although it's not included, if I bought no oranges, it would cost me $0. So I am going to say let's start with 0. And then it looks like every orange is going to cost 60 cents, right? So 60 cents for buying 1 orange, 2 oranges would be $1.20, and so on. At 60 cents an orange, 3 oranges would be $1.80, 4 oranges would be $2.40, 5 times 60 would be $3, and so on, as I buy more oranges. Again, though, it's just a discrete list of values, intermediate values. Like there's no way I'm going to pay $1, because that would be more than 1 orange but less than 2. That wouldn't make any sense. So a specific list of values in my range here. All right, so that was how I might express domain and range for that discrete function. Let's take a look at how I would do it for the continuous function, where we had the time and the temperature of the water. Now I only gave you the specific ordered pairs. Oops, sorry, I'll move that so you can see it. I only gave you these specific ordered pairs, but we know we could measure temperature at any in-between value. 1 minute, 5 minutes, 8.6 minutes, right? Any of those. So when I go to do my domain, m, the number of minutes, could be as low as 0, and then it would keep on potentially. Excuse me, it's warming up. Let me try that one more time. I was thinking we were putting the water in the fridge there for a moment. Oh, I'm on minutes. Sorry guys, lost my focus. Let me try that one more time. Yes, the smallest number of minutes would be 0. 0 minutes after it leaves the fridge. And then technically speaking, it could go on and you could let that water sit out there forever, right? So I'm going to say, m is greater than or equal to 0. There is really no upper bound on that. M can be any number greater than or equal to 0. Now notice I didn't list it this time. I can't. I can't list all of the possible fractions and decimals. So I simply use the inequality notation and say any number of minutes bigger than 0 would make sense in this problem. What about the range? Well, let's see, the range. The temperatures, the lowest temperature is 35 degrees, and the water's going to keep on getting warmer from there. Now, we don't really know what room temperature is. We'll talk about that more in just a minute, but certainly the water's not going to get any colder than the 35 degrees that it was when you took it out of the fridge. So I'm going to say T is greater than or equal to 35 degrees. Now this time, if I want to be a little bit more realistic, I might say, well, really, it's unlikely that that water is ever going to get to be 500 degrees, not just sitting at room temperature, right? That doesn't make sense. So in actual fact, the temperature probably has an upper bound. The problem didn't give me enough information to really determine the upper bound, but I might say the water is never going to get any warmer than the temperature of the room. And if the problem had given me room temperature, I could fill in an exact value there. If I want to guess, I might say, room temperature maybe about 70 degrees. If I make that assumption, then I can actually put an upper bound on my range as well. All right, so again, contrast here. In a discrete function, you'll have to list the specific values of domain and range. In a continuous function, you'll have to use inequalities because it's not possible to list all the fractions and decimals that would be possible values of your input and output. All right, we have one final example to wrap up our section 1.1 here. Up until now, every problem that I've given you has been given in the context of a specific situation. Cost and oranges, time and temperature, children and their heights, right? They've all been in context. Sometimes, however, you, I'm sure, know that sometimes mathematical relationships can be defined without any context at all. And in that case, unless the variables are given to you and told, specified in the problem, you're really free to choose your own. Typically, the default variables that we choose are x for the input and y for the output. But unless I tell you that, if you really want to pick two different letters here, you could. I'm not going to. I'm going to use x and y. But again, unless you're told differently, you could choose anything you want. So I'm going to say, let's assume that these are all of the form x comma y. X being my input then, and y being my output. All right, does this set of ordered pairs represent a function? Well, I need to show, if it's going to be a function, that every input just has one output. So just quickly looking in turn here, when the input is 2, I don't see input 2 anywhere else here, so the only output for 2 would be 7. 4, again, it's not repeated as an input, so only output is 10. 5, the output has to be 3. 8 is 7, and 9 is 1, right? So the problem that you might occur is if you've got the same input multiple times leading to different outputs, then you'd be in trouble. You would not have a function. But that doesn't happen here. So I'm going to say yes. Each input x has just one output y. All right, we want to write function notation to represent the set of ordered pairs. And this time, they gave me a letter that they want me to use to name the function. So if I got free choice, I might have just said y equals y of x, but they want me to use the letter f instead. So the output y is f of the input x, right? Output equals the function name of the input variable. All right, the next question is to find f of 4. So they gave me the input, x equals 4, and I need to find the output that goes with it. So coming up here in my list, when x is 4, the output is 10. Take just a moment and determine what is f of 9. So we're being told here that x is 9. When x is 9, the output is 1. By the way, if you aren't sure, remember, the 4 is in the same position as the x, so you know they're telling you the x. Again, 9 is in the same position as the x. You know they're telling you the x. It's also possible for me to tell you the output variable. In E, find all values of x. So we don't know the input, such that f of x equals 3. Notice here, the 3 is actually in the same position as the y, right? It's on the equal side. It's not on the f of x side. So what's happening here is I'm being told that y equals 3. And I need to find the value of x. Well, looking back at my list of ordered pairs, right here I see a y value of 3. And in that case, x is 5. Okay. Again, take just a moment and see if you can answer the next question. f of x equals 7. So we're being told that y is 7. And coming up to my list, that actually happens twice, right? X is 7, excuse me, y is 7 here, and also here. So x equals 2 and x equals 8 would both be solutions here. So finding all values of x, I'm going to tell you both. X equals 2, x equals 8. And that's fine. It's possible for two x values to have the same y. That's okay. You just can't have the same x value, giving you two different y's. All right, is this a discrete or continuous function? In this case, when it's not in context, the best we can do is answer based on the information we have. And in this case, the only x values that I know the output for are 2, 4, 5, 8, and 9. I don't know outputs for any others. So I'm going to have to say discrete, simply because if x was 2.7 or 3.5, I wouldn't know what the output is. That means that when I ask in part H about the domain, I'm simply going to list the values of x, my input variable. So my domain would be the values of the input variable. 2, 4, 5, 8, and 9. Again, notice discrete, so it's a list. The final question, what is the range of f? Range, that's the value of the output variables. And again, I'm just going to have a list. 7, 10, 3, 7, 1. You don't have to, but I tend to like to put them in order. So I might go with 1, 3, 7, 10. Even though the 7 occurs twice, I don't have to list it twice. So just 1, 3, 7, and 10. All right, so that is a wrap on our first section, 1.1. All of the functions that you'll see in this particular section will be defined numerically, either through a table of values or a list of ordered pairs. Next time we'll take a look at section 1.2.